Okay, so in the last video we had gone up through number 3 and I had suggested that you might want to pause the video and try the next bunch of them on your own. So let's go over those together now. So here in number 4 we see that we have the power rule. We have an expression here raised to the second power, so we know that we're going to take this outside exponent of 2 and multiply it by all of the inside exponents. And we're remembering that the 2 inside the parentheses needs an exponent of 1 on it. So we're multiplying the exponents, remember, not the base. So we have 2 to the second power, b to the negative 6th power, c to the 10th power, d to the 8th power. We remember that our instructions asked us to put all of our answers having only positive exponents. So we know that we are going to keep 2 squared where it is, keep c to the 10th where it is, keep d to the 8th where it is, b to the 6th will go down to the bottom to be positive. Now you can leave it like this. In this case, 2 squared is such a simple number, it's just 4, so I would probably change it to 4 there, but either one is fine. Okay, and the next one, we have a combination of a couple things. We have d squared, and then d to the 4th to the 5th. And remember, we talked about this before, that the exponent only goes with whatever it's right next to. So d to the 4th is what's being raised to the 5th power, that's all. And you can kind of think of order operations in a way where I need to do those exponents first and then multiply. So I have to do that part first. So I'm going to have d squared times d to the 20th. Okay, I multiplied 4 times 5. Now I have an example of the product rule. I'm going to add those exponents and get d to the 22nd. You can picture this. If I were to write this out, I'd have d times d, and then d times itself 20 times, so all together I would have 22 of them. So similar idea over here. In this case, both parts have an outside exponent. So this first expression is being raised to the 4th power, and the second expression is being raised to the 2nd power. And then once I've done that power rule, then I can combine any instances of b and c that I have. Again, I'm going to go through and include a 1 as an exponent for anything that doesn't have it. So that would be the 3 and the b here, the b and the c in the second expression. So now I multiply those exponents. So 3 to the 4th, remember it's not 12, it's not 3 times 4, it's the exponent times 4. B to the 4th, c to the 20th. So at any point that you are not sure exactly how we did something, go ahead and pause the video, work through it in your head. Ask me if you have questions. B to the 2nd, c to the 2nd. So now I'm going to work with the product rule, right? So I have 3 to the 4th, and then I'm looking at my b's. So I have b to the 4th times b squared, so that will be b to the 6th. And then I have my c's also working with the power rule, the product rule at this point. So I have c to the 20th and c to the 2nd, which is going to be c to the 22nd. Now in this case, I don't have any negative exponents, so I can leave it like this. Or 3 to the 4th, again, 3 times 3 is 9, 9 times 3 is 27, 27 times 3 is 81. You could also switch that to there. Either one is fine. Okay, looking down at number 7 and number 8 on here. Here, I have some parentheses, but they're really just to show multiplication. There's no power rule happening here. These are just 3 different expressions. They all have the same base, so with like bases, I can add the exponents. So if I add negative 4 plus 4 is going to be 0, and then 0 plus negative 5 is going to be negative 5. Okay, so a to the negative 5th is what I get when I add those exponents. Well, I need to change that because it's a negative exponent, so I'm going to put it on the bottom, and I need to put a 1 on the top of that fraction as a placeholder. All right, number 8. So remember when I'm doing the quotient rule, if I subtract, I always subtract top minus the bottom, and the answer is going to go on top when I do that subtraction. So in this case, I would take 5 minus 12, numerator minus denominator for the exponents. I get x to the negative 7th. Answer goes on top, meaning it's just x to the negative 7th, or x to the negative 7th over 1. Now, if I want to change it to a positive, then I put that down on the bottom as a positive exponent. And with this one, if you think about what's happening behind the scenes, my numerator looks like this, right? These are all being multiplied. Don't really need those dots, but just for clarification. The denominator has 12 x's being multiplied together. Let's see if I get 12. 4, 5, 6, 7, 8, 9, 10, 11, 12. So I can cancel x on top with an x on the bottom. So I cancel out 5 of them. What I have left are 7. So if you think again about each of these becoming a 1, there's my 1 on the top, there's my x to the 7th on the bottom, right? It's like wherever the positive exponent is going to end up wherever the leftovers are going to be. So it's kind of another way of thinking about it. Okay, so we have a few more here. Let's see, we did 13 in both classes, but we can go through that also a little bit. But let's really concentrate on 9 through 12 here. So in this case, we have a quotient, we have a fraction being raised to the second power. So this is an extension of the power rule. Every inside exponent gets multiplied by every outside exponent. So, or by the outside exponent, I should say. So we have m to the 6th over m to the 10th. And then I can now use the quotient rule. 6 minus 10 is negative 4, which would be the same as 1 over m to the 4th power. Now, there's another way you could do this. So here's version 1 of this. Version 2 is that you can also do this simplifying inside first if you would like. So if I think about what's inside the parentheses, m to the 3rd over m to the 5th is m to the negative 2nd. Then I can multiply that, get m to the negative 4th, get 1 over m to the 4th. Okay. You could also switch this to 1 over m to the 2nd first and then do it, but there's a couple different options. So with these kind of problems, really you have more options that you might think. For number 10, I can see that I don't have any like terms on the top, like bases, that I can use the product rule on, but I can use the quotient rule. So 3 minus 8 is going to give me c to the negative 5th. This is one of these ones that I would suggest writing out. So 7, it's not 7 minus 1, it's 7 minus negative 1, which is 7 plus 1, or 8. So it's going to be d to the 8th power. And you can kind of picture that, because if I had moved this up to the top, if I had taken this d to the negative 1 and moved it up to the top first, then it would be d to the 7th times d to the 1st. I add those exponents, there's my d to the 8th. So now I want to do my decisions of what I keep there, what stays and what moves. So d to the 8th will stay, c to the 5th will move down to the bottom. Okay. This next one, the 0 right here, should send off some alarm bells in your head. So this whole thing is being raised to the 0 power. That means that whole thing just equals 1. So I'm just going to rewrite everything else with that 1 for now. It's not that the exponent becomes 1, it's that the whole expression becomes 1. Now, do I really need this 1 since I'm multiplying by other things? No, right? But we can just kind of put it there. For now, I just put it there to remind you that these two things are the same. That and this are the same thing. Okay. Well, now I can multiply these. 2, because there's nothing else to multiply it by. Add these exponents, x to the negative 3rd. This is an example. We talked about this when we first talked about some negative exponents. 2 has an exponent of 1 on it. So that's going to stay where it is. That has a positive exponent. The negative 3 is only on the x, So that moves like so. Okay, going on to number 12. We may have done number 12. I think we did it in one of the classes, but not the other one. So if you have already done 12 and 13 in your notes, you can even skip ahead on the video a little bit if you'd like, or you can watch them again. So I have some quotient rule going on here, right? I have x and x, top and bottom. And then I have y and y. And I have z and z, right? There's nothing, none of those variables have two expressions on the same part of the fraction, so I can't use my product rule, but I can use the quotient rule. So I'm going to just bring down my 5. 5 is being divided by 1 in essence, right? So 5. This is where we want to write out what we're doing, okay? I can almost guarantee that at some point there will probably be a mistake. I would make a mistake if I just tried to rely on what I'm seeing, because your brain wants to add those instead of subtracting. So for x's, my subtraction is -3 minus -2, which is like -3 plus 2, which is -1. So x to the negative first. Y, 5 minus 1, right? There's a 1 on that y, not so hard. That's 4. Z, 1 minus -4 is 1 plus 4, or 5. And then I switch things around so that everything is a positive exponent. So 5 stays, x to the first goes down to the bottom. I can write the 1, I don't have to. Y to the 4th stays, z to the 5th stays. And in class, at least in the class we did it in, we talked about how if you wanted to move things around first, if you wanted to move these individual expressions from top to bottom first to only work with positive exponents, that's okay also. All right, so let's do a quick review of number 13. So again, we have some instances of the power rule here. So this thing, this expression on top is being raised to the -2nd power. This first expression in the denominator is being raised to the 0 power. And this second expression in the denominator is being raised to the -3rd power. Okay. So, and again, I'm going to go through and include a 1 as an exponent for anything that doesn't have it. So that would be the x in the first part, the 3 and the y in the second part, and the 2x and y in the third part. That just reminds me also, especially with the numbers, it reminds me that I'm multiplying by the exponent, not by the number itself. Okay, so now I'm going to multiply. So x to the -2nd, y to the -6th, z to the 4th. Now, the yellow part here, we know that anything raised to the 0 power is 0. So, anything raised to the 0 power is 1. So that's just going to go away. That's just going to become 1. Now, if you forget that and you multiply these, you still would get 3 to the 0, x to the 0, y to the 0. So hopefully at that point you'd think, oh yeah, 1 times 1 times 1, right? So either way, as long as you remember eventually. And then here we're going to have 2 to the -3, x to the -3, y to the -3, z to the -12th. The 1 I don't really have to keep writing because there's other stuff being multiplied by it. If I think about now some quotient rule, so I have my x and my x, I have my y and my y, and I have my z and my z. Okay, so that's what's going to go together for the quotient rule. I also have this 2 to the -3rd, that's just going to stay a number, right? And we'll kind of deal with that some more later on. So again, I would very strongly suggest that you write out what your subtraction is for the quotient rule. So -2 minus -3. Get all your negatives and your subtraction in there. -2 plus 3 is 1. So first I'm just going to do my quotient rule and write what I get up on top here. And then if I need to move things around, I will. So that's x. Y is going to be -6 minus -3. negative 6 plus 3, which is negative 3. So y to the negative third, and then z, 4 minus negative 12, 4 plus 12 is 16. So z to the 16th over 2 to the negative third didn't move. So now we do our normal test of what's going to stay and what's going to move. So x to the first, or just x, is going to stay. Z to the 16th is going to stay. Y to the third moves to the bottom. And 2 to the negative third moves to the top. And then I'm just going to rewrite this and clean it up a little bit. We usually put our numbers first. So 2 to the third, x, z to the 16th over y to the third. Or you can change 2 to the third to 8, right? It's not 6, it's 2 times 2 is 4 times 2 is 8. Either one of those is fine. So again, as we talked about in class, this is just the same rules over and over, right? Power rule, product rule, quotient rule, just putting them together. So when you look at one like number 13 that looks a little crazier, you don't have to know exactly every step that's coming. Okay, you kind of have to know, okay, how do I start? I always start with those parentheses and that outer exponent. So start with that and then take it one step at a time. All right, so moving on to scientific notation. So scientific notation is a way to write very large or very small numbers in a more compact and easy to read way. Okay, that's what it says there at the top. So the reason, some of the situations where we use scientific notation, think about science, it's right in the name. Let's say you're an astronomer and you are measuring the distance between stars. Very, very large numbers, right? Or if you are a microbiologist and you're measuring the measurements of DNA or something, right? Or parts of, molecules. So, very, very small numbers. So scientific notation, it's easier, especially if you're working with those numbers a lot, rather than having a number, like this, for a really large number, and having to every time think, okay, let's see, that would be millions, billions, trillion, what is that? Or if you have a really small number, and having to think about what place value that's in. If you work with these numbers all the time, instead, we could say that this is 4.5 times 10 to the 15th, or this is 1.6 times 10 to the negative 8th. Okay, if you work with these numbers all the time, especially, then it's really easy, and you can compare things easily. If I have two numbers written out with a whole bunch of zeros, I'm trying to compare them, that's really hard. But if I say 4.5 times 10 to the 15th versus 3 times 10 to the 10th, it's easy for me to compare them more quickly. Okay, and I realize not all of you are going to be astronomers or microbiologists or whatever, and that's fine. This is just sort of the basis behind some of the scientific notation. So we want to have our numbers, if they're going to be in scientific notation, they need to be in this format right here. So a times 10 to the n. A and n are my numbers that I'm going to find. Okay, every scientific notation is going to have that 10 in there. So a is a number between 1 and 10. It can be 1, it can't be 10. So in other words, another way to say that is that a has exactly one non-zero digit in front of the decimal point. And we'll see an example of that. And then n, my exponent, is going to be an integer. It can be positive or negative. Okay, so let's take a look at, before we get into scientific notation, I want to kind of do a little bit of review of what these powers of 10 they're called, right? So these are all called powers of 10. 10 to the first, 10 to the second, 10 to the third. Let's think about what these are going to be. So 10 to the first, anything to the first power is just that number. 10 to the second power is 100, because it's 10 times 10. So actually, let me rewrite this the other way. Okay, so 10 squared is going to be 10 times 10, which is 100. 10 cubed is going to be 10 times 10 times 10, which is 1,000, etc. Okay, you might see a couple patterns here. First of all, obviously the exponent tells me how many times I'm multiplying. It's also, when it works with tens only, it also kind of, in this little trick, tells me how many zeros there are after the 1. Okay, so 10 to the third is going to have 3 zeros. 10 times 10 times 10 is 1,000. So you can see that this is getting bigger by 1 0 every time. So 10 to the fourth is going to be 10,000. And again, that's not just pulled out of thin air. That's what I get when I have 10 times 10 times 10 times 10. 100,000, a million. Okay, so let's take a look at this for just a minute over here on the side. And I'm going to rewrite some of these. I'm going to just start with 1,000. Excuse me. So I have 1,000. And then next I have 100, and then next I have 10, so here's 10 to the third, 10 to the second, 10 to the first. Well, what if I kept up with this pattern? My exponents are going down, so what if I kept up with that pattern? Like that. Okay, so 10 to the third is 1,000, 10 to the second is 100, 10 to the first is 10, 10 to the 0 power, well, we know that anything to the 0 is 1. And it kind of follows our pattern anyway, right? 10 to the third has 3 zeros, 10 to the second has 2 zeros, 10 to the first has 1 0, 10 to the 0 has 0 zeros. And I'm moving over, my 1 is moving over one place value to the right every time. It's getting smaller by a factor of 10. So if I'm going to continue that pattern here, what has to happen? Well, it has to keep going to the right. But remember, there's a decimal point right there. So what happens now is if I'm going to keep this pattern going, I would have to move over into the decimal places. And every time my 1 would keep getting moved over one place. Okay, so here's my pattern. My exponents are going down by 1. My number gets moved over every time one more place value. Well, what is this? If I look right here, what's this, another word for this decimal? Let me write it in another color here. This decimal is also known as 1/10. This decimal is also known as 1/100th. This decimal is also known as 1/1000th, right? 10th, 100th, 1000th. This is also known as 1/10,000th. We'll take a look at those denominators. Those look kind of familiar, right? 10, 100, 1,000, 10,000. Those are powers of 10 on the bottom. So let's now also think about what do we know about negative exponents. Let's go back to this printed outline here. 10 to the negative first. We know that's the same as 1 over 10 to the positive first, which is just 1/10. Same as what we got when we looked at this pattern. 10 to the negative second is 1 over 10 to the second, which is 1 over 100. 10 to the third is 10 to the negative third is 1 over 10 to the third, which is 1 over 1,000. These are getting smaller. Imagine that there's a cake, and I'm going to give you 1/10 of that cake. That means that I cut the cake into 10 pieces and give you one. Well, 1/100th means I'm going to cut that cake into 100 pieces and give you one. Or cut the cake into 1,000 pieces and give you one. They're getting smaller and smaller. So 10 to the negative fourth now is going to be 1 over 10 to the fourth, which is 1/10,000th. This is going to be 1 over 10 to the fifth, which is 1/100,000th. 10 to the negative sixth is 1 over 10 to the sixth, which means 1 millionth. So now imagine I take that same cake, instead of just cutting it in 10 pieces and giving you one, I'm cutting it in 1,000,000 pieces and giving you one. So you get one tiny crumb. So that's obviously much smaller than 1/10. Okay, so thinking about these positive exponents, right? 10 to the first, 10 to the second, 10 to the third, etc. Those give numbers that are big. 10, 100, 1,000. So if I were to take something and multiply it by 1,000,000, I'm going to get a bigger number, right? Well, these numbers that have the expressions that have negative exponents, they give me little numbers, less than 1. They're fractions, 1/100th, 1/1000th, 1/1,000,000th. If I have $3 and I want you to give me 1/1,000,000th, or I want to give you 1/1,000,000th of what I have, I'm not giving you $3. I'm giving you a tiny part of it. So when I multiply by a fraction that's less than 1, I'm going to get a smaller number. And that brings us back to scientific notation, okay? So here's why. Some people, when they teach scientific notation, want you to remember, okay, if it's a negative exponent, we're going to move right, we're going to move left, or whatever. And I don't ever want you to do that. I want you to be able to think through why I would be using a positive exponent or a negative exponent. So here's our little rule we're going to use. If it's a big number, if my plain, and this will make sense in a minute, if my plain old number is a big number, which means simply that it's greater than 1, it goes along with a positive exponent. And if I have a small number, which simply means less than 1, I have a negative exponent that goes with that, okay? And you'll see what this, so this is all that we're going to have to remember. And then we can understand each time whether there's positive or negative exponents. Okay, so I want to write this in scientific notation. Remember, that means a times 10 to some power of n. So first of all, I look at this number. This is a plain old number. It's called standard notation or decimal notation. It's not in scientific notation yet. I need to put it in scientific notation. So when I look at this, I know I want to have just one number, one non-zero digit in front of my in front of my decimal point when I'm done. That's going to be the A part. So my decimal point starts out at the end if it's not written in. And I'm going to count over until I put my decimal point in such a way that there's only one non-zero number in front of it. So for example, if I moved my decimal point right here, I would still have all of this in front of the decimal. It's not a number between 1 and 10. So I want to keep moving it over. Now, I will say that saying that I'm moving the decimal point is really bad, lazy math on my part. I'm really not moving the decimal point, right? What's really happening in essence is, if you can picture these numbers like on cards, I'm sliding it over to a new place value. So the decimal point is staying the same. I'm moving my numbers over to a new place value. But the lazy way to say it, which I probably will when we're talking about this, is that I'm moving the decimal point. So I'm going to keep moving until the decimal point is in a place where there's just one non-zero digit in front of it, which is right here. So I get 5.4. I don't have to write all those zeros when they're after a decimal point. So here's my number between 1 and 10. So the compact way to write this is 5.4 times 10 to some power. Okay, well, the number for your exponent comes from how many moves you made. So 1, 2, 3, 4, 5, 6, 7, 8. So I know now that I have plus or minus 8. I don't know if I'm going to have positive or negative 8. And that's where this rule comes in. My original number was big. It was bigger than 1. As a matter of fact, it was 540 million. That's definitely bigger than 1. That tells me that I need a positive exponent here. Okay, so let's think about why that is. That's because 10 to the 8th is going to be 100 million. So 5 times 100 million is 500 million, right? If I had a negative 8 here, I would want 1/100 millionth of 5. That's going to be a little teeny tiny part. So imagine money. If I have a $5 bill and I want you to give me 100 million of those, that's a lot of money. If I want you to give me 100 millionth of that, split that $5 bill into 100 million pieces, that's going to be a really little tiny piece. Well, my number here, my 540 million, is a big number. Okay, let's look at this one. This number is bigger even. It's 3,783,000,000. So again, decimal point needs to go where there is just one non-zero digit in front of it. So 3.783 times 10, I moved it 3, 6, 9 places. It's going to be positive because it needs to represent a big number. All right, what if I have these two now? And again, I'm asked to put these in scientific notation. So now I do see my decimal point here. So there's a 0 in front of it. I want to move it until there's one non-zero digit in front of it. That would be right here between the 4 and the 7. So my A to get between 0 and 1, or sorry, between 1 and 10 is 4.72. I moved 1, 2, 3, 4 times, so I know I need either a plus or a minus 4. Remember my rule, small number, less than 1, which I clearly have here, gets a negative exponent. So again, it's 10 to the negative 4th is like 1 over 10 to the 4th, which is 1/10,000th. So 4 is getting multiplied by 1/10,000th of it, and that makes a little tiny number. Same idea here. My decimal point would go here. It's going to be 1.9 times 10 to the negative 2nd. Okay, now we're going the other way. We're going to write in standard notation. So we're going to take a number in scientific notation and write it in standard notation. And again, we're going to think about that rule to decide which direction we have to move our decimal. 10 to the 6th, that's a big number, right? That's a million. So if I want to take 4 and multiply it by a million, which I know is a big number, it has a positive exponent, then think about what direction I have to move to add on enough zeros in the right way to make a million. I'd want to go this way. Okay. Now, when I get to here, I've run out of numbers, but I still need to move my decimal the rest of the way. So 1, 2, 3, 4, 5, 6. So 1, 2, 3, 4. Those empty places fill in with zeros. So to clean this up, I have 4, 7, 3, and 4 zeros. I put in my commas from the right-hand side, and I get 4,730,000. Right? 4 times a million is 4 million. Okay, same idea here. I have 9.2. I have a positive exponent, so I'm going to go this way because that will give me a bigger number. I have 2 spots to fill in with zeros. I have 9,200. Now we have some negative exponents. That tells me that I'm going to want to make a smaller number. If I moved this way, I would be making a bigger number. So I want to move this way. 1, 2, 3, 4. There's my decimal. So these 3 are going to be zeros. And to make it neater, I always put a 0 in front of my decimal also. So I have that. Then I have 3 zeros, 1, 6. Tenths, hundredths, thousandths, 10,000ths, 100,000ths. This is 16 hundred-thousandths. Okay, next I have 8.123. Again, I see that I have a negative exponent. That tells me I want to make a smaller number. So I'm going to move it to the left because that's what makes a smaller number. So I have 0.08123. Okay, so that's the end of our scientific notation. Okay, kind of a long definition of it, but I want you to really understand it and not just think of it as sort of this process that you don't understand. So I am going to actually stop this video so I can upload it, and then I will do one more to cover the last few pages.